Hello, in this video, my colleagues and I will be discussing the research we conducted at the University of Calgary during the winter 2020 semester for a project entitled Spectra Studies with the RAO Echelle Spectrograph. In this project, the spectra of the Sun and the Orion Nebula was captured using the Echelle Spectrograph at the Rothney Astrophysical Observatory located near Pritis, Alberta. A CCD camera was used to capture the digital spectral images of these two targets. These images were then processed using three different software programs. The first was Mamer Pro, which was used to media and combine the raw images to create a best final image. The second program was called ISIS, and it was used to flatten the curved spectral lines of the images in order to aid the spectral analysis. Additionally, in ISIS, three calibrations were used to improve results. The first was the tungsten calibration, which was used to find orders in the target spectra. Secondly, an LED calibration was used to illuminate and locate higher orders of the spectrum. And finally, the thorium-argon spectrum was used to calibrate the wavelength of the different spectra being studied. Finally, last but not least, in visual spec, a heliocentric velocity correction was applied to the spectra. This was done in order to account for the rotation of Earth during the time of observation. Visual spec was also then used to analyze the absorption lines in the spectra, which correspond to various known elements.
Determining the composition of the Sun from its spectrum, the emission lines obtained from the solar spectrum were compared to the known emission lines of various elements. Any overlap confirmed the presence of that element in the Sun. However, not all the absorption lines present in the solar spectrum indicated their existence in the Sun. Some of the absorption lines were introduced by the Earth's atmosphere, which are also known as telluric lines. Using the H2O correction feature in visual spec, we were able to distinguish between telluric lines and the actual absorption lines. Also, the H2O correction feature gave us a modified green-colored line curve, which is shown in Figure 1. In the end, only two elements were confidently identified in the Sun: hydrogen and helium. Rest of the elements, such as carbon, nitrogen, and oxygen, were suspected to be arising from the Earth's atmosphere.
The third column of our poster contains a more specific look at M42 and our findings concerning it. And the Orion Nebula is one of the brightest nebulae in the sky, is about 1,300 light years away from us. Despite this distance, you're still actually able to see the Orion Nebula from Earth with the naked eye. Looking further at our column here, in Figure 2, you can see median combined image of M42 spectrum, which was obtained from the spectrograph. Using this spectrum, we were able to determine that the hydrogen alpha emission line in the 34th order sat somewhere around 6,562.3 angstroms. Using a rest wavelength for hydrogen alpha of 6,562.8 angstroms, we were able to determine the radial velocity of M42 that sat around 7,771 meters per second. Now, because our hydrogen alpha emission line is shorter than our rest wavelength, we can also determine that we have a blue shifted wavelength, which means that M42 is moving towards the Sun at that 7,771 meters per second. Now, this also shows that Doppler shifts of emission lines can be used to determine radial velocities of astronomical objects.
The temperature of the Orion Nebula was determined by studying the forbidden lines pertaining to doubly ionized oxygen and singly ionized nitrogen. Forbidden lines refer to the emission of a photon due to prolonged time periods between two collisions in a very low density gas that is prevalent in a nebula. These lines were identified in the spectrum of the Orion Nebula by determining their wavelengths given in the books by Donald Osterbrock and Cromie. The intensities of the corresponding wavelengths were then entered into a formula provided by the radiative transfer theory in order to calculate the temperature, which came out to be between 8231 and 9705 kelvins. The spectroscopy has led to a great many discoveries, from determining the chemical composition, mass, temperature, radial velocities of stars, to locating exoplanets that are situated light years away from us. Thank you, and hopefully you enjoyed our presentation.